Every year, industries around the world lose billions of dollars, not to market changes or equipment failures, but to silent, invisible corrosion. In the oil and gas sector, pipelines, storage tanks, and offshore platforms slowly degrade. Leaks, unexpected downtime, and catastrophic failures cost millions and threaten lives. Corrosion is not limited to oil and gas. Across manufacturing, power generation, transportation, and infrastructure, it quietly damages critical components, driving maintenance costs higher, causing production delays, and increasing safety risks. Despite all technological advances, most inspections are still manual, reactive, and prone to error. Small signs of deterioration often go unnoticed, allowing minor issues to escalate into major failures. The financial impact is staggering. Experts estimate that global industries lose over $2 trillion annually due to corrosion and material degradation. Beyond dollars, there's the cost of safety hazards, environmental damage, and downtime, which can ripple across entire supply chains. What if there were a way to detect corrosion early, assess its severity, and predict its progression before it compromises safety or leads to costly repairs? What if inspections could be smarter, faster, and more precise, empowering engineers and operators to take proactive, data-driven actions instead of reacting after damage has occurred? This is the challenge we aimed to solve, turning what is invisible into knowledge, what is reactive into proactive, and what is costly into preventable. Was there any solution that we termed global or universal? No. How much oil must be spilled? How many gallons of oil must be lost before we act? 1 million of gallons? How many lives must be put at risk before we take corrosion seriously? Why do we still rely on reactive maintenance when predictive technologies are already within our reach? What if corrosion could be detected early, before it compromises safety, before it leads to costly failures? Imagine a system that not only identifies corrosion in its earliest stages, but also helps prevent it altogether. Today, we're excited to introduce our innovative Vision AI solution for corrosion detection, a smarter, faster, and more reliable approach to ensuring safety and sustainability. Traditional corrosion analysis often depends on manual observation, a process that is slow, inconsistent, and prone to human error. This manual approach not only delays detection, but also increases the risk of unexpected failures that can compromise safety and cause costly downtime. Our team set out to change that. We've developed an AI-driven corrosion analytics platform built and tested in Google Colab that makes corrosion assessment faster, smarter, and far more reliable. Using the power of computer vision, image segmentation, and statistical surface mapping, our system automatically detects and quantifies pitting density, surface roughness gradients, and differentiates between uniform and localized corrosion zones, all in real time. The platform then generates a comprehensive analytical report containing detailed quantitative metrics, corrosion morphology patterns, and data-driven insights into underlying electrochemical mechanisms. But we didn't stop there. Each analysis goes beyond detection. It includes AI-assisted recommendations that link observed corrosion patterns to root causes, material degradation rates, and targeted mitigation strategies. This means engineers don't just see corrosion, they actually understand why it's happening and how to prevent it. The platform itself is lightweight, cloud deployable, and requires no local installation, making it fully accessible from anywhere in the world. It's scalable, efficient, and easy to integrate into existing maintenance workflows. During our live demonstration, the algorithm analyzed real corrosion images, extracting mechanistic insights and delivering predictive guidance for both maintenance scheduling and design optimization. After each image analysis, the system exports a detailed failure analysis report highlighting predicted causes of corrosion. Our findings revealed 2 key causes in this case: chloride and sulfide contamination, leading to localized electrochemical pitting corrosion, and iron oxide formation from moisture and oxygen exposure, especially where protective coatings had deteriorated. These combined factors emphasize the critical need for predictive monitoring and proactive maintenance, which is exactly what Coro LLM Vision AI is built to deliver. With Coro LLM, we're bridging the gap between visual inspection and intelligent corrosion management, turning raw observation into actionable intelligence, and transforming how industries detect, predict, and prevent corrosion failures before they happen.
To further validate our model's accuracy, we conducted a controlled test using two steel coupons, one visibly corroded and the other in good condition. We mixed them together and let Coro LLM analyze both simultaneously. Within seconds, the system distinguished between the corroded and clean surfaces, precisely highlighting affected regions and confirming real-world reliability. After this lab test, we moved to an industrial setting. We captured a live image of a chiller, an actual machine under working conditions, an image never used during model training. The goal was to see how well Coro LLM performs on unseen data. It not only detected corrosion accurately, but also adapted to complex lighting, textures, and environments, proving its consistency even outside the lab. Coro LLM's performance on real-world images means inspectors and engineers can make instant, data-driven decisions with clear visual evidence, right where it matters most. From lab tests to live inspections, Coro LLM bridges research innovation and real-world corrosion management.